The atomic mass is the mass of an atom of a particular element. So for example, the average atomic mass of hydrogen is 1.01. The average atomic mass of nickel is 58.69 atomic mass units. The average atomic mass of potassium is 39.1 atomic mass units. And this system of atomic mass units is based off of carbon-12. Now, carbon-12 was assigned by scientists an atomic mass unit of 12. And the reason it was assigned as 12 atomic mass units is because carbon-12 is made up of 6 protons and 6 neutrons. And protons and neutrons weigh almost exactly the same thing. Neutrons weigh slightly more than protons. See if I can remember the weight of each one. Proton is 1 point... It's either 7.6 or 6.7. I think it's 6.7. Whatever. It's not really going to make much of a difference either way. 672 times 10 to the minus 27 kilograms. And a neutron has a 4 instead of a 2. And if these 6s and 7s are reversed, I honestly can't remember. Oh, this is kilograms. And even if they are reversed, still, the point is that this tiny difference in weight is negligible. So for carbon-12, they say that the protons and neutrons are essentially the same mass, and therefore it is assigned 12 atomic mass units. And the rest of the elements' atomic mass units are assigned by the ratio of their mass to carbon-12's mass. So for example, carbon-13, its atomic mass is assigned by the ratio of carbon-13 to carbon-12. So I have some mass of carbon-13. And now this is assuming that there are the same number of atoms. So if I have the same number of carbon-13 atoms as the same number of carbon-12 atoms, now I just take the ratio of their masses. And I looked this up. This is found to be equal to 1.0836. So it doesn't matter what the mass is, as long as they're equal. It's found the ratio, and carbon-13 is found to be 1.0836 times more massive than carbon-12. That's what this ratio means. So now to find carbon-13 in atomic mass units, I replace mass of carbon-12, which is with just 12 atomic mass units. Oh, I forgot to mention that atomic mass units is abbreviated by AMU. And now this is a very simple algebra problem. Multiply both sides by 12 atomic mass units, and I find the mass of carbon-13 to be equal to 13.0036 atomic mass units per atom of carbon-13. And this works for any element. If I wanted to compare oxygen, I would take the mass of a quantity of oxygen and compare it to the mass of the same quantity of carbon-12. Find out what that ratio is, and then multiply both sides by 12 atomic mass units, and then I would have that oxygen in atomic mass units. And that works for any element and any isotope of any element. And that's what these numbers are. Now, these numbers aren't quite exactly the atomic mass of a particular element. What these are the averages of the atomic masses of an element. For example, carbon exists in different isotopes. Many elements exist in different isotopes. So when an element exists in different isotopes naturally, then in order to avoid having to make two separate calculations, an average is just taken. So for example, hydrogen exists as a proton and an electron, or there is such thing as deuterium, which is a hydrogen atom with a neutron. Normal hydrogen is just a proton and an electron. This isotope of hydrogen is a proton, a neutron, and an electron. And same thing with carbon-13. Carbon-12 is normal carbon, and then carbon-13 is carbon with an extra neutron. Carbon-13 would be 6 protons and 7 neutrons. And that occurs naturally as well, but they occur in different ratios. So what happens is that scientists just take an average of it. So for example, always easiest to illustrate with an example. Carbon-12 in the universe occurs %98. So in the universe, naturally occurring carbon is carbon-12 98.89% of the time. If I was to take all of the carbon in the universe, 98.89% of it is carbon-12. And the other commonly occurring carbon is carbon-13, and that is 1.11% of the total carbon. There are other isotopes of carbon like carbon-14, but that is a radioactive isotope, and while it does occur naturally, it does not exist in any significant quantities because it's radioactive, it's unstable, and it decays. And that's the same thing with many other isotopes. While they do occur in nature because they're radioactive and unstable, or they occur in such small amounts that they're essentially negligible. And in this case, carbon-14 is basically negligible. So when I take a scoop of carbon just at random anywhere, including at my own body, let's say, out of every 100 atoms, 99 are going to be carbon-12, and one of them is going to be carbon-13. And that's the same with almost any carbon compound. It's going to occur in this ratio. So in order to calculate the average atomic mass of carbon, I need to take the percent of carbon-12 plus percent of carbon-13, and then I get the natural carbon. So, in order to find this, I can convert this directly into a decimal, or I can just add 98, or I can take it as 98 atoms in one atom and then divide by 100. I'm just going to convert this to a decimal. And this is for carbon-12, and carbon-12 has an atomic mass of 12 per atom. And I'm going to add it to 0.0111 of carbon-13. And earlier I found carbon-13 to be 13.0036 atomic units per atom. And then I do this math and it will be equal to 12.01. This is atomic mass units per atom. And if I go up to my chart, I look at carbon, it is 12.01. So let me do one more example where I'm looking for the average atomic mass of a particular element. Suppose I have a mass spectrometer and it finds that for every 100 atoms of natural copper, .09% are copper-63, and 30.91% are copper-65. What is the average atomic mass and suppose that the atomic mass of copper-63 and copper-65 are already given. Copper-63 is 62.93 atomic mass units per atom. 65 is 64.93 atomic mass units per atom. And I want to find the average. And this is exactly the same problem as the one above. I'm going to convert these to a percent. So I have .6909. Convert these percentages to a decimal, or I could just do it the other way. I suppose I did it the decimal way the first time. I'll do it this way, the other way the second time. So if I have 100 atoms that go by, 100 atoms of natural copper. So for every 100 atoms of natural copper, 69.09 are copper-63, and the atomic mass of copper-63 is 62.93 atomic mass units per atom, plus I get 30.91 atoms of copper-65, which has an atomic mass of 64.93. And this is going to be equal to the total atomic mass. So I get 69.09 atoms, multiply it by this, atoms are going to cancel out, and then I just get this multiplication. Same here, atoms are going to cancel out, and I'm going to be left with atomic mass units. And if I do this multiplication and addition, I'm going to get 63.5, and then I round it up 5 AMUs. Now if I want to know this is 65,000, or 6,355. I went ahead of myself. So I have 6,355 atomic mass units. Now if I want to know the atomic mass units per atom, I counted 100 atoms, 69.09 atoms of copper-63 and 30.91 atoms of copper-65. So I divide by 100 total atoms. And I get natural copper is equal to 63.55 atomic mass units in an atom. And had I converted these percents to a decimal right away, I would not have had to divide out by this 100, because the 100 would have already been factored in, or the division of the 100 would have already been factored in. And if I go to the periodic table, I find copper 29, 63.55, and that is the value which I attained. And that's how all of these atomic masses are found. They are found by comparing the elements ratio to carbon-12. That way the discrepancy between protons and neutrons is not that important. That's why when we calculate for, say, copper-63, it's found to be 62.93, and the reason it's not an even number is because protons and neutrons don't have exactly the same mass. But in a ratio, that's not really that important because it's going to be multiplied, so that's fine. And after that is found in order to find the average atomic mass, which is what is important, because people don't want to do two separate calculations. They don't want to have a separate atomic mass for copper-63 and copper-65. What scientists have done was just said, well, naturally occurring copper exists 63% or 69% as copper-63 and 30% as copper-65, average them together, and then the need to calculate separately is eliminated because it's an average.